Now, let's see the concept of Cholesky decomposition, which is one of the very essential phenomenon in the world of finance, especially when we have to do simulations. In lots and lots of applications of finance, we use simulation, and wherever the simulation of the correlated data is required. If I want to simulate independent one single variable, it's a very easy process. But if I really require not independent but interrelated kind of variables, probably if I want to simulate A and B data in such a way that the correlation between A and B is 0.5. If I want such kind of information to be generated, I have to rely on Cholesky decomposition itself. So just to talk about, wherever the idea is to do a simulation of the values, especially for portfolio VAR computation, or we have so many option products, exotic options that have been created even for valuing many of the exotic options which are very heavily dependent on basket of products. They are very much useful. Even if I have to simulate something for credit default swaps on a basket of loans, all these where we really need to evaluate the portfolio which have interrelationships between them, and I have to simulate that kind of a data, we are relying on this process of Cholesky decomposition itself. And just to understand how it works, first we take the variance covariance matrix. In any case, if I have to do a Cholesky decomposition, I have to go with a variance covariance matrix. Let me just take that. We'll try to see what we can do with that. So now going ahead with this particular data set, I'll take the returns, right? I'll take the returns of these three companies. The data has been provided, so I can very well compute the returns based on the daily data. Alright, so I'll take the logarithm of this value divided by this value to arrive at the daily returns. So coming out with these numbers being my daily returns. Now I need more than any of these things, I need the variance covariance matrix. So as I need the variance covariance matrix, I really would be interested more only in that aspect at this moment rather than computing any other stuff. So here I am computing the variance of ICICI Bank, I am computing the variance of Tata Motors, I am also computing the variance of the Reliance. And similarly, I am taking the covariance between the ICICI Bank returns and the Tata Motors returns. Similarly, I am taking the covariance between ICICI Bank returns and the Reliance returns. Similarly, I am also taking the covariance between the Tata Motors returns and the Reliance return. So more or less these are the numbers that I am considering, and this is more or less equal to this is more or less equal to this, and this is equal to this. So let me just quickly put it in a percentage form so that we can understand the things better. So these are the correlations that are getting, these are the covariances that are getting operated between each of the different companies. Okay, so this is my variance covariance matrix. Now what we are simply saying is, when we are doing the Cholesky decomposition, this variance covariance matrix, we are going to split it into two matrices. One is called as a lower triangle, one is a lower triangle matrix and the other one is an upper triangle matrix. So the lower triangle matrix is nothing but which is having zeros in the upper part of the triangle. So this is what is my lower triangle matrix. And the same I take my upper triangle matrix ABD 0CE 00F. So this is my upper triangle matrix. What this Cholesky decomposition says is you take your matrix, variance, covariance matrix, whatever is there, 0.052%, 0.019%, 0.018%, again 0.019, 0.018, then it is 0.047, here you have 0.028 and one more number 0.011. So this is your variance covariance matrix, right? Variance covariance matrix, you are able to write it in this form, find out A, B, C, D, E, F, solve for them, and this is very much possible only when this variance covariance matrix is definitely positive definite. When we are saying positive definite, I take any vector W which could be any weights. What we are simply saying is the W transpose multiplied by this variance covariance matrix multiplied by W at any point should be positive only. Then we call it as positive definite. If it is greater than or equal to 0, we call it positive semi-definite. If it is less than 0, we call negative definite. And if it is less than or equal to 0, we call negative semi-definite. Now, for this Cholesky decomposition to work, the matrix with which we are doing this job should be a positive definite matrix. And now we know variance, covariance, at any point of time, whatever the weightages that we are multiplying with, the transpose of this multiplied by this, we know that it is the definition of variance, and variance cannot be negative. So we are under the clear impression that this particular matrix is definitely positive definite. If not positive definite, it is positive semi-definite to any extent. So this is what we are simply solving to typically arrive at and mapping it with this matrix to typically arrive at A, B, C, D, E values. So simply this is becoming A squared, that's it, and this is becoming AB, this is becoming AD, this is also AB, this is B squared plus C squared, and this is becoming BD plus CE, and here it is becoming AD again, and this is becoming BD plus EC, and the last one is becoming D squared plus E squared plus F squared. So this is the typical thing that is coming out. So the first thing we can easily solve, A squared equal to 0.052 percentage. So from this I can find out my A. So probably if I am saying that this is my lower triangle matrix and this is my upper triangle matrix, the first few things in the lower triangle matrix, definitely these threes are zeros, and in the upper triangle matrix I can refer to this particular value, this to this particular value, and this to this. So up to here it is known. Now in the lower triangle, I am able to find out my a, which works out to a square equal to this one. So I can very well find out my a, which I am taking as square root of this. So the square root of this, so even here I'll take this as my a. This is the square root. Then the next thing which we are bringing out is, we know, now that we know a, we take these two things. AB equal to this much. So I know a, so I can find out b. So b is nothing but AB divided by A is going to be my B. So here all I am going to take is AB, which is this number. I am dividing it by A, which is this number. So I know that this is the value of B. So in the upper triangle matrix also, it's going to come out to be this number. The same logic I can apply to D. This is AD and I divide it by A. So this comes out to be the D. So here also this is my D. And a few more things coming out here. AB is done. Now B squared plus C squared. B is already known. So C squared will be whatever this number minus B squared. This number minus B squared, and square root of that is going to give me this. So I'll take square root of this number, which is B squared plus C squared, right? This is this number which is equal to B squared plus C squared. I subtract B squared from it. This is B squared. I subtract this and I take the square root of it. So this is going to be my C, and here also I am going to refer to the same C. So here C is known. Now BD plus CE is going to be this number. BD plus CE. Now B, C, D, all three are known. So this number minus BD divided by C is going to give my E. Alright. So what is that I need to take? This number minus BD. BD. So this happens to be B. This happens to be D. This number minus BD divided by C, which is this, is going to be this particular number. So this number I can very well link it here as well. Now only one variable, D squared, E squared, F squared. So from here I can subtract the D squared as well as the E squared. So here from this I take the square root of, from this number I subtract D squared minus E squared and I take the square root of it, which is giving me this particular. Now all these, this is what we call as a lower triangle matrix, and this is an upper triangle matrix, wherein the upper triangle is 0 is called as the lower triangle matrix, and the lower triangle is 0 we call as upper triangle. Now every variance covariance matrix can very well be composed in this way. Now whenever we are able to compose it in this particular form, break it down and compose it in this particular form, that is what is really generating. Now I can use this to typically generate the return, which are more or less linked in the same way. Now that I have the variance covariance matrix, based on that I was able to break it down into the lower triangle matrix and upper triangle. That is what we call as Cholesky decomposition. Now let's say if I have to simulate the returns of these three. Right now I want to simulate the returns of these three. Now what are those average returns of these three before I really get in, because I have to generate even the averages also in the same manner. Based on the average value and the correlation between them is what I would take as the base to typically move forward in terms of their generation. Now I know these are my average returns of each of them. This is the lower triangle matrix and this is the variance covariance matrix. Now, as a part of the simulation process, what generally happens is we try to generate some random variables. Now, because I need three, for three of them initially I will go ahead with the generation of the random variables based on the standard normal distribution. I'll use the norms inverse function, or probably in 2010 and more we have norms S inverse function. Both of them are one and the same. I take the rand as the probability. Now I got these three as one instance of a normal random variable. Now the same logic I can continue for a good number of simulations. Now I have generated so many values for a simple simulation purpose. So all these possibilities I really want to see. I want to generate the returns for ICICI Bank, Tata Motors and Reliance. Now what is that I need to do? At least for one of them, if I want to check out for corresponding to this, what is my returns here? If these are the random variables, I multiply it with their corresponding corresponding Cholesky decomposed matrix, and I typically do an M mult. I do the multiplication of this with this. I do the multiplication, matrix multiplication of this with this. A 3 by 3, a 3 by 1, giving me a 3 by 1 matrix. So I'll directly take this, comma this, and I do a control shift enter. So this is going to be the returns on one single day, which will go on doing this kind of matrix simulation. I mean, which will follow this kind of variance and covariances. This kind of variance and covariances linking with this particular, these are the numbers that are getting generated. So this becomes one instance. The same logic I have to continue for all. And this is only with respect to variance and covariance. So that's the reason for whatever that got generated, we will also add up, right? For these numbers that got generated, we should also add up these transpose of the returns, because I have taken the returns in this way. I'll also add up the transpose of these returns as well. And here also I will fix this particular matrix. Right, this entire thing, let's say I'm doing this, it means that I have considered this plus the addition of these returns as well. So it will generate the returns as well as the variance and covariance corresponding to this period. Now what I'll simply do is I'll drag it here. So this is the mean, this is the return of this is the return of this. For each of the instances, I'm getting different kinds of returns. The first one is for ICICI Bank, then for Tata Motors, and the last one is for Reliance. Now let me drag it till the last to observe what has really happened in this process. Let's try out whether our objective is getting met or not after doing this much of simulation. So we have got so many returns being generated just by looking at the data. Now let me try out through this mechanism what is the kind of return that ICICI average return which ICICI Bank has generated. The average return which ICICI Bank has generated, yes, it was slightly a negative. Probably if I had taken, it came out to minus 0.05%. Right, let's try out if this is the case with the other two as well. Yes, they have generated 0.17 and 0.17% kind of return. But when I go with the correlation between them, the correlation between the ICICI returns the correlation between the ICICI returns and this is working out to 0.4, and probably I can even take the covariance just to see whether the covariance matrix has more or less worked or not. Okay, the covariance is coming out to 0.00139. The same logic we can execute between. So this is the kind of a simulated returns that we are typically coming out with based on the normally distributed random variables. So this is how we can break the variance covariance matrix into the constituents so that we can very well generate a lower triangle matrix as well as an upper triangle matrix. Use the lower triangle matrix in conjunction with the returns so that we can very well generate. See, the intention here is use this data to generate the value at risk. Use this as an input for valuing the exotic options. So such kind of workout can very well be done. That's how the matrices play an important role even in generating simulated returns of the more and more resembling kind of variables. So let me try if let me try we can freeze this as well. Right, we'll freeze it because once we have generated a normal random variables, it's better that we freeze it. Okay, this has generated this kind of a return. This has generated different kinds of covariances between each of the return. You'll find more or less appropriate to the numbers. But of course, because here we have assumed that the data is more and more normal in nature, we are getting slightly different sets of observations. It might very well happen that the returns of ICICI Bank may not be purely normal in nature. If I look at the skewness, yes, there is some skewness in case of ICICI, some skewness in case of Tata Motors. Even if I look at kurtosis, I see that the kurtosis is very positive here and very positive in all, which means there could be a few extreme values that are present in the data. So if I really have to bring out much more normality into the data and a proper reflection of all these, I can very well ensure that my data is very close to normal as well. That could even more improvise the process of generating the data more and more appropriate, because we have, while simulating, we have taken a normally distributed random variables, whereas in reality these values are not fully normal in nature. That's a small difference that could very well exist as a part of our simulation. But here the entire understanding is we can use the concepts of matrices to, and that too especially Cholesky decomposition, to typically arrive at a simulated set of variables which can really help in terms of a set of variables which are more and more correlated and which can help in generations of the variables which are having correlations in between them, right?